Well, hello to everyone. Thank you for having me. I'm really excited to be here since this is my first time speaking at an event as big as this one. My name is Mihailo Ilic. As you can see, I have multiple affiliations, but today I'm here on behalf of the Visler Labs Foundation to talk about scalable and interoperable data flow management for digital twin frameworks in smart farming. Now, there's a lot going on in this title alone, which is why I'm going to immediately point out three keywords. The first one is interoperability, the second one is digital twins, and the third one is smart farming, because this is what we will be focusing on the most during today's talk. Okay, let's start off with defining interoperability. So what is interoperability? This is the ability of software systems to communicate with one another seamlessly and to share their data in such a way that allows them to work together to solve some common issue or to work towards a common goal. There exists genius hardware and software solutions in almost every domain today, but they have not reached their peak performance because they usually operate in silos, so they operate in isolation. If we want to make them as best as they can be, we need to make them be able to talk with one another more effectively and efficiently. So in other words, we want to address this lack of interoperability between systems in order to maximize their potential. One domain which is battling this issue today is smart agriculture. Now, you may have heard the term smart agriculture before, and there are some enabling technologies which actually put the word smart in front of smart agriculture, right? And these technologies are smart sensing and monitoring, data analysis and planning, and also autonomous farm management. When you put these three technologies together, you can get some sort of smart system in the agricultural domain. So we're aiming for smart decision making, and for smart decision making, the key is to optimize the data collection process and to use monitoring to your advantage, right? So we want to make those smart decisions, and interoperability can help us with the problem of data collection and data transfer, right? So interoperability in agriculture can do multiple things. First of all, it can reduce costs. It can then minimize operational overhead. And most importantly, from my perspective, is to create optimal user experiences. Why did I single this out? Because creating optimal user experiences is actually what drives adoption rates up. So you want people to start using these kinds of systems to actually help them, right? But you need to first make this experience desirable for them. So how can we achieve interoperability? Well, essentially through two aspects. There are multiple levels of interoperability, but today we'll be focusing on two key aspects. The first one is semantic interoperability, and semantic interoperability implies using some sort of ontology or at least a common vocabulary to define entities and relationships in the problem domain. So in our case, I'll be talking today about agriculture, so we want to have a common vocabulary on agricultural entities. And on the second thing which helps make systems more interoperable is the use of a common syntax, which is syntactic interoperability. So essentially, you want to define how the various software components in some system, how it represents the data it's handling. So you have to have a common syntax, essentially. One key thing about interoperability, it's best if it originates as close as possible to the data sources. This eliminates the need for some higher level interoperability middleware. Let's move on. Now I would like to introduce you to the Horizon 2020 Smart Droplets project. This project gathers 9 organizations all across Europe, and the idea behind the project is it views smart farming technologies as key enablers in the reduction of chemical use during agricultural operations. So we want to reduce the use of chemicals in agriculture, and the project's activities will be validated in 2 sites in Lithuania and Spain, on wheat farms and on apple orchards. Conventional spraying methods are one of the most resource-intensive agricultural operations that there are out there. So each year they compromise various aspects of agriculture, like natural resources, chemical resources, and also human resources each season, right? So we want to minimize the use of these chemicals. Because of this, the EU Green Deal has been proposed, and it states that there is a goal of reducing pesticide use by 50% and fertilizer use by 20% by 2030. So this is not that far away. And the idea behind smart droplets is to advance both hardware and software capabilities during chemical application, right? So this can be done through the use of data collection and actionable digital twins to make predictions and make some suggestions on what's the best course of action to take in order to maximize yield, but also to minimize the use of chemicals. Apart from this, which we will be focusing on the most, some other aspects of the project is to advance edge technologies in regards of edge AI and robotics components, which will be utilized in the project. There are multiple technological building blocks which are associated to the project. First and foremost, there's the data infrastructure. So this is the core of the interoperability framework that we will be developing in the project, and its main goal is to enable interoperability. This is key because we will have a lot of hardware and software components which will be communicating with one another, and we need to ensure that they can do that in the most efficient and effective way possible. Apart from this, in the cloud, we also have AI models and digital twin services. And these are the main intelligence components of the project, and they are the ones that will actually drive the decision-making process in the entire system. They're also located in the cloud, as I said, but on the edge, we also have robotic systems. And these systems include autonomous vehicles and autonomous sprayers, which collect data and actually apply those actions which are suggested by the digital twin services themselves. Last but not least, we have the direct injection spraying system, which allows us to apply high precision spraying in the field, essentially, which directly influences the reduced use of chemicals in agricultural operations. On this slide, you can see a general overview of the project architecture. Now, we're not going to go too much in depth into this. I would like to just point out here that, as you can see, there's a lot of communication going on between various components. So we have field data sources. We have third-party services like weather apps. We have intelligence components in the cloud, right? And we also have autonomous field systems, which are like vision systems and autonomous sprayers, autonomous vehicles like tractors moving through the field, etc. So as you can see, there's a lot of data moving through the system back and forth, and we need to optimize this communication, right? This is the key. So because we have a lot of components here, we have to make those components communicate as simply as possible. Let's talk a little bit about actionable digital twins. So digital twins essentially give us the power to have virtual counterparts of real-world entities in the cloud. By doing so, we could actually run simulations in the cloud and see what are the best strategies that we can implement in real life to actually maximize or minimize some actions, right? We want to, in this scenario, we want to maximize yield while minimizing chemical use. So for this goal, we're using WFOST, which is short for World Food Studies. And this is a mechanistic model for simulating crops and simulating the spread of diseases, for example, or the spread of pests in the field, etc. And this model is developed and maintained by our partners at the Wageningen University in the Netherlands. So what can digital twins bring to the project? Well, they can bring a couple of things. I'll list them out here. So first and foremost is precision spraying. That minimizes environmental impact directly, right? It can do some predictive analysis, so we can, if we notice there's some presence of disease in the crops in the field or some pests, we can predict whether or not and how the spread will continue. We could optimize resource use, which directly reduces operational costs, and we could also have our end users, in this case the farmers, have access to remote monitoring from anywhere. Digital twins entail that you imply that you have actually essentially like a live feed of data going into the application, and you can in real time monitor what is happening in the field. Okay, so as we said, the digital twins are the main decision-making component of the entire system, right? Because of this, we want to feed as much data possible to that system so it could give us the best possible suggestions on further courses of action, right? As for the data sources that we have, our main data source is the autonomous field systems, right? These autonomous field systems send data continually to the cloud to be processed. Apart from this, we also have third-party services. For example, we would like to have information on weather, on what's the weather going to be like tomorrow, 2 days from now, 3 days from now, etc. This data is also key. One of the most important data sources that we could have is actually manually submitted by farmers themselves. So the system, the main goal of the system is to provide suggestions on what to do next, right? If we have direct feedback from our end users, from farmers, this is valuable information, right? Which can directly influence how the digital twins and simulators work in the future. Apart from this, if for some reason on some crop or on some field or on anything, we don't have enough data, we could always create a data source from legacy data sets, and then we could fill that in and use it to try and solve the cold start problem before it even causes any issues for us. Okay, now let's talk a little bit about autonomous data collection, since this is the main data source in the project. So the main edge component, which does data collection in the field, is the Smart Droplets Vision System. It essentially is a set of cameras, RGB cameras and stereo cameras, which are mounted on retrofitted autonomous tractors. So these tractors move through the fields on their own, and while doing whatever they need to do, usually, right, they also do data collection with these cameras. These cameras are also accompanied by some edge AI, so we have a couple of AI models aboard the tractors as well. And these AI models are used to detect weeds, detect pests, predict if there are nitrogen deficiencies anywhere in the field, and they can also do plant canopy density assessment. Now we'll go over each and every one of those just quickly to see what the idea behind all of this is. So pest detection is done using RGB cameras. You have some images here, so you can see on your own. While the tractor moves through the field, it continually scans the canopy in order to try and search to try and find some pests on the leaves or on the branches or anywhere. And if it does detect them, then it geographically stamps the location and sends that stamp to the cloud, or in other words, to the digital twin services. By stamping the location, we know where we have to apply some, let's say, medicine later on, right, to the crops. Weed detection is also is similarly to the previous example done also using RGB cameras with its own dedicated AI model, and it's also georeferenced as well. So if weeds are detected, we stamp that area and move on. Okay. Nitrogen deficiency can be identified by discoloration of the plant leaves, right? In our case, if there is nitrogen deficiency, the leaves become more yellow. So this can also be done by RGB cameras simply, right? If we detect yellow leaves, we can mark the location as being nitrogen deficient, and later on we can apply some precision fertilization to that area. As I said, last but not least, we have canopy density estimation. So what is this essentially? We have a set of stereo cameras, and these stereo cameras have the ability to do some 3D essentially scanning of the canopy, which are the leaves and the branches and everything of the plant, right? And by doing so, you can create an estimate of how dense the leaves and branches are, and see what the volume is. So by doing so, we can actually have a trace of where the crop is doing the best or the worst on some given field, right? So based on this, we know where we need to apply precision fertilization if need be. So now that we've gathered the data, let's see how the decision-making process actually goes. So the actionable digital twins, what do? They are given data, and from this data, they extract some sort of information. And this information, through the use of some simulations, they extract knowledge from this information. And this knowledge is then used to actually give us some optimal actions on what to do next in order to maximize or minimize certain goals, right? I'm reminding you again, we want to maximize yield while also minimizing chemical use in every aspect, right? The general workflow is as follows. So field level observations are uploaded to the data management platform. Sources include sensors and third parties, farmers themselves, autonomous field systems, and whatnot. And then this data, after it's uploaded to the digital platform, it's forwarded to digital twin and AI services, which are also hosted somewhere in the cloud, right? The decision-making process is then done there at the end of the digital twins, right? So it's really hard to use this. Okay, so at the digital twin and AI services, we may have the main decision-making components, and the output is sent back to the autonomous tractors, in this case, for further actions to be taken, let's say tomorrow, maybe. Okay, now that we've covered the data flow, the decision-making process, and everything, I think it's time to move on to interoperability, just to comment, to go over this concept. So high-level system interoperability can essentially be implemented through two concepts, right? The first concept, as we mentioned, is semantic interoperability, and semantic interoperability means that we want to use some sort of common vocabulary at the minimum, or ideally an ontology which covers all of the concepts related to a specific domain, so all of the entities and all of the relationships between those entities. Apart from this, the second concept is syntactic interoperability, which is an agreement on a common way of representing data. So how do we encode this data and how do we move it around the system so that everybody knows what we're talking about, right? Full semantic interoperability is hard to implement. The main challenge right here is that you usually have to work with some sort of legacy systems, and these legacy systems can be difficult at times to move to some different way of operating or doing things, right? So we want to move them to a more interoperable way of doing things. There is a middle ground. For this project, we did choose some middle ground, which we will comment on a bit later. Okay, so semantic interoperability, what this does. It increases communication efficiency between numerous systems, and it actually brings in a common terminology on the concepts of a given domain. In our case, this is agriculture, right? Ontologies, what they bring us. Ontologies, they provide some sort of shared understanding of concepts and relationships in a domain, and they allow us to formally represent these concepts in some way or another. When you're developing an interoperable system, it's usually a good idea to do some research and check out if there are some ontologies which are already defined somewhere else, which can cover most, if not all, of your use cases, right? So what did we do? We thought about what are all of the entities and all of the relationships in the agricultural domain. So for instance, we've identified farms, fields, and crops, fertilizers, soil, some tractors because we have autonomous tractors moving through the field, sensors because we have vision systems, right? And so on. And apart from this, we also have some sort of events which are crucial to us. So sowing and harvesting are events which are crucial. We also want to know about irrigation activities, pesticide application, fertilizer application, and so on. So to this end, we've actually went with the smart data models, which is a collaborative effort to support the adoption of common data models. This effort is led by the FI-Ware Foundation, among others. Since it's a collection of vocabularies, essentially, we've chosen one vocabulary from this collection, which is the Smart Agri-Food vocabulary. It covers the domain of agriculture, naturally, and it's one of a great number of vocabularies in this Smart Data Models initiative. So here we can see that we've actually identified, okay, this is just like a tabular view of what are the mappings between real world entities and those entities which are described in the vocabulary that we're talking about right now, which is the Smart Agri-Food model. So for instance, we've identified farms, fields, crops, and let's say some irrigation events, for instance. In the right column, you can see their equivalents in the Smart Agri-Food model. So a farm is described as an agri-farm in this ontology or in this vocabulary, for instance. Fields are described as agri-parcels, crops as agri-crops, and so on. So you get the idea, right? Apart from this, we're not only using the smart agri-food model because, as I've said before, we also have in the project robotics components, some vision systems, some autonomous sprayers. So we do need some other vocabularies to fill in what we're missing. We're missing the smart robotics and smart sensing vocabularies at this stage, so we are also including them in the project as well. Generally speaking, the smart agri-food vocabulary works the best for us because it covers most of the use cases that we need. It's only going to require a little bit of an expansion from our end to cover 100% of what we need. So if you're developing some kind of interoperable system, do your research, it will save you a lot of time. Now that we've covered semantic interoperability, it's time to move on to syntactic interoperability, which poses the question of how should the data be represented. Okay, so the smart data models, they go hand in hand with NGSI-LD, which stands for Next Generation Service Interface Linked Data. Now, NGSI-LD is both an information model and an API specification. It's used to facilitate the seamless exchange of data between components, and we'll see how it does this. NGSILD, if you want to encode your data in some fashion, right, to some format, NGSILD is an extension of the standard JSON-LD format, right? So this is really good for legacy systems, which usually rely for communication. They usually rely on standard REST APIs, right? So we're still using JSON here to transmit the data, which is ideal. NGSI-LD describes entities as having properties and having relationships to other entities as well. And these properties and relationships, they actually come from contexts. And in our case, the context is the smart agri-food context, right? So, for instance, we could view some crop, right? A crop has a property in its name, but it can also have a relationship to the soil it's planted in. So it has a relationship to its soil, and it also can have a relationship to some fertilizer which is being used on it currently, right? So it also has a relationship to some fertilizer, as we can see on this graph right here. Apart from this, at the core of the data management platform is the Orion Context Broker, which acts as some sort of interoperability hub in the entire system. So this is an open source component which is also maintained by FIWare, and its goal is to enable the seamless communication between different systems. In our case, it's placed in between the cloud intelligence components and the edge components, which include the vision systems. They include the autonomous sprayers and so on. In the cloud, if you recall correctly, we have the digital twin services, the AI services, and the simulation services, which are all interconnected, and they need to speak a common language in order to be effective, right? This is just a quick slide to illustrate the differences between the JSON-LD format and the NGSI-LD extension of the JSON-LD format. So let's just take a quick look. On the upper left, we have a definition of some person. So this person has an attribute in its name. It also has its birthday, right, as an attribute, and it has an attribute named spouse, which is essentially a relationship to some other person, right? On the bottom right, then, we have the same person translated from JSON-LD to NGSI-LD, and it looks a bit more complex, right, at this point, but it's not really scary. So it only is a bit more verbose in a sense that all of these attributes that we see have a little bit more of metadata available. So, for instance, if we look at the name attribute here, it has a metadata property of type, which defines it as a property, essentially. The born attribute also is of type property, and the spouse attribute is of type relationship because it represents a relationship to some other entity, which is another person. Okay, now that we've covered all of this, the data collection, the decision making, and how the communication works interoperably, we can take a look at an example use case, right? So we have a wheat farm down below. This wheat farm has 2 fields, and it has one autonomous retrofitted tractor, which has all of those vision systems we've talked about during the presentation. In the cloud, we have multiple components. At the core of everything, we have the data management platform, which hosts the Orion Context Broker. It also has a data warehouse, and it has some other digital twin and AI services off to the side in the cloud as well. So what happens? we have this autonomous tractor. It goes out into the field, and while doing what it does, it simultaneously collects data about weeds, about pests, about the nitrogen deficiencies, and about the plant density, essentially. This data is then transformed into the NGSI LD representation that we've talked about when the tractor goes back to base. And this NGSI LD data format is then transmitted to the data management platform. At the data management platform, these entities are stored in the data warehouse and then are made available to the digital twin and AI services. What happens here? Well, we run simulations on the virtual counterpart of the field in question, right? So we try applying various levels of pesticides, various levels of fertilizers and everything, and we find what works best. The output is a set of actions in NGSI LD format, which is sent back to the autonomous field systems to be applied maybe later today or tomorrow or at some later time. To conclude, there currently exists a noticeable lack of interoperability between systems in numerous domains, and because of this, we are missing out on the full potential of our apps, right? Essentially, because of this, we need to address this issue and make them more interoperable and more efficient in solving bigger issues, right? We've seen that multiple levels of interoperability also exist. However, you have to be smart when implementing interoperability because there is no one-glove-fits-all solution to every problem, right? You have to analyze your problem and see what are the pros and cons of each level of interoperability you want to implement, as we have made a decision to not go, for instance, for full-level semantic interoperability, but to use only a vocabulary level of interoperability. The Smart Droplets project aims to advance smart farming and to reduce the use of chemicals during agricultural operations. And interoperability is seen as an accelerator of this because we have multiple software components and hardware components which can work more effectively if they speak to one another more easily and effectively. This is all that I prepared for today. My name is Mihailo Ilic. If you want to talk about the project or anything else for that matter, you can either contact me through LinkedIn, email, or just talk to me during the coffee break. No problem.